When you graduated, was it 2012?
Yeah. Okay. So, the great things and talking about some of recent very interesting. Well, it's not appeared yet, so to appear work, all functions and to use.
Thanks a lot, Bert. It's great to be back as always. I hope to continue learning over and over. So, yes, as Per mentioned, I'll be talking about some work which is to appear soon. So, well, let's get started. Ignore the word L functions for a moment. One of the goals of my work, I think a lot of us, is to try to resolve the fine structure of high energy spectra in 2D CFTs and or the structure of black hole microstates in quantum gravity in IHES or otherwise, but I'm a holography guy, I'm a grad student. So I think about CFTs, and so by resolve fine structure, I mean go beyond classical or semi-classical statements and say something about microstates. Now, what does the bootstrap say about this? So far, not much. Most results are coarse-grained, either say averaged over energy in some sense, even the Cardi formula is a result of this type, or work in Lorentzian regimes where some parameter like the spin is becoming large, and so you can constrain the spectrum of 2D CFT regimes of large spin in a very precise fashion, and sometimes say something more than just coarse-grained, but there's no general understanding of this type of question, whether you're in 2 dimensions or higher dimensions. And so that can be phrased in the form of a question: in what sense do bootstrap principles constrain the heavy spectrum of conformal primaries, say, microscopically, or at least their endpoint autocorrelation, some statistical all orders understanding of the correlations amongst the heavy states? Then how does that happen? And so to me, this suggests the following idea, which is that we should find and solve constraints that act just on the high energy states. Whereas a lot of what we know about the high energy spectra of 2D CFTs comes from branching low energy data to high energies using crossing or modular invariance. What we want to understand is whether there are constraints that just act among the high energy states and can help us resolve the details of the high energy spectrum. So today I'm going to propose that thinking about 2D CFTs in the language of L functions is useful for this. And I will spend some time to explain what L functions are, not assuming so much familiarity with that, although everyone here knows about the Riemann zeta function, so you do know about L functions, whether you know that or not. But before doing so, let me just motivate why we'd want to construct L functions for CFTs. Well, L functions, as I'll try to hint at later, the zeros are famously studied, and they exhibit myriad measures of chaos and random matrix statistics, which are things we want to understand about the CFT spectra of interest, and that we don't, that are surely intimately tied together with the questions I was posing earlier. So are they useful for that, either in some literal sense or just as toy models? L functions are often and conjecturally always attached to automorphic forms of one type or another, and we don't understand very well properties of the non-holomorphic modular functions relevant for 2-dimensional CFTs. In particular, for the partition function on the torus, this is a modular invariant object, and if the CFT spectrum is generic or chaotic, we don't have any examples in hand, even of partition functions that have these properties. They're all more like something like the modular J function, where there's a regular spectrum of operators in the CFT sense. So can the L function language somehow help us with this? Just on the math side, they have many intriguing properties, and there's some resonance with physics intuition for several of them. And turning things around, if we can understand this, we might provide the mathematicians, the number theorists, with some sort of objects which seem a bit exotic to them, which can be interesting. And these objects are guaranteed to exist just by the existence of CFTs themselves. So today I'll focus on 2 dimensions, as you've already figured out from the title. Modular invariance will be critical in this, so it's hard to see how a higher dimensional extension holds. At least I haven't thought about it. And while these grander ambitions about finding patterns of high energy are still, to be realized, one thing I'll focus on is this kind of question that kicked off the whole so-called modular bootstrap program, which is the following. In a unitary 2D CFT, how heavy is the lightest non-vacuum primary allowed to be? So how much can I push up the lightest non-trivial state in the theory, say as a function of the central charge of the theory? And these are some plots from some works on this subject, which are upper bounds on the dimension of the lightest, say, Virasoro primary operator in your theory. And so I'll recall the existing bounds, briefly sort of explain the history of that, why they're believed to be suboptimal based on arguments from gravity, and explain how L functions can be used to improve those bounds. So if you don't take anything away from the talk as far as results, I'd be still happy if you took away the overall themes, which is that there's a new way to think about torus observables in 2D CFTs that I think will be useful. I hope to demonstrate that it already has been useful. That we can think about modular invariance in a slightly different way, and that there might be some new proof strategies for bootstrap type questions that could be helpful. So I'll talk mostly about partition functions for Virasoro CFTs, but I'll mention some generalizations briefly. The Virasoro CFT, I mean,
Can I ask a very dumb question?
please.
So why are you particularly interested for the torus?
Well,
Like some other metaphor.
Well, if I want to count local operators, then I compute the torus partition function. So from that point of view, it's a natural thing to do. But also I know that 2D CFTs exhibit the local observables on the torus are modular covariant. And so there's this extra SL2Z structure that we can use. And that's a powerful thing. So I want to try to use it.
It's better than S2, for example.
Yes, yeah. Well, for one thing, there's a local operator interpretation, but that's kind of the main physical question that when I do the trace over the Hilbert space of eta minus beta H, that's something that lives on the torus, and I want to count those states and ask it like this. Okay. So Virasoro CFT is language by which I mean there's no extended chiral algebra, but you can treat that case too. Okay, and this actually leads to some open questions about how to define random matrix universality in 2D CFTs. I won't really have time to talk about that today, but suffice it to say for now that in bootstrap approaches to 2D CFT, we don't usually know how to add that information that the theory is chaotic or random, or even understand what statements are supposed to hold for generic 2D CFTs. And I'll have something to say about that toward the end, but probably not time for much. Okay. So the outline, I'll explain a bit about what I've gleaned about L functions from some of my reading, although it will not be a comprehensive overview because I'm not capable and because the subject is huge. Then we'll talk about their construction in 2D, which doesn't take very long, and then some of their properties. There will be a brief interlude, if I think there's time, to explain how a certain form of random matrix universality in 2D CFTs can be viewed, translated into this L function language, into something called subconvexity, which I'll explain in a few minutes, which is sort of intriguing from the L function side. And then onto this modular bootstrap question, and finally, probably just a few words about this. Okay, so notation-wise, tau is x plus iy. This parameter s, which will be sort of trade the tau dependence for s dependence when you work with L functions, just like zeta s. So I'm taking s to be sigma plus it, x, y, sigma, and t are all here. Please interrupt with questions at any time, and well, let's get on. So a kind of bottom-up definition of an L function that I think is reasonable to a physicist is that it is a generalized Dirichlet series, that is a sum of coefficients divided by some numbers to the s, that meromorphically continues to the whole complex S-plane under a certain type, a very particular type of functional equation, and perhaps possessing other special properties, depending on what kind of mathematician you are. So an ordinary L function, L of s, takes this form. These ANs are the interesting data, with the coefficients that are general complex, divided by this n to the s here. Now what's called the completed L function is the following thing, you multiply this by some so-called gamma factor, gamma of S, which is just a product of d gamma functions with these so-called spectral parameters kappa. These are just again some complex numbers. And also some overall numerical factor like q to the s over 2. That's again just some convention. This q is called the conductor, but no matter. The point is that when you construct this combination, this thing has poles only at 0 and 1 and obeys this functional equation. Under s goes to 1 minus s, it picks up a phase called the root number, and in general is related by some complex conjugation, where this lambda bar is called the dual L function, which in the Dirichlet series language means that you just complex conjugate the coefficients. An L
So
function.
I think the
yeah.
poles that are on this part of the definition of it. So. In the ANs we put them that way. That's the part of the definition.
Yes. Also from the ANs, you wouldn't expect anything like this to hold. An L function where it is related to itself, rather where in other words, where it equals where it's real, is called a self-dual L function. In that case, lambda s equals lambda 1 minus s times some number, which is plus or minus 1, this root number. Okay, so the classic example that we all know is the Riemann zeta function. So if we form the so-called completed Riemann zeta function lambda, the notation I use is lambda of s over 2. You take Riemann zeta and you multiply it by these factors. This is invariant under s goes to 1 minus s. In other words, it's a self-dual L function of degree 1 with unit conductor root number plus 1 here, and kappa 1 is 0. Okay, so just a few comments that I think are relevant. L functions are often attached to automorphic forms. This word attached is the word mathematicians seem to use. So if you have some holomorphic or non-holomorphic modular form with maybe some weight, you have just sort of written this schematically. There's some association between that and some L functions where in the Dirichlet series, the coefficients are the Fourier coefficients of the form. Okay. And the modular property of this is essentially just translated to the functional equation of the L function. So the relation here, this makes it seem like this is some simple translation, but actually like math, deep math in trying to find or establish that there exists an L function which obeys a functional equation attached to a certain type of modular form with a certain weight for a certain group. Standard L functions, like the Riemann zeta function, also have an Euler product. So typically there's a product over all the primes P of a factor like this. The alphas are some other coefficients, not the A's, they're just some other coefficients. Some degree D here, again, the same degree that I mentioned before. So you have some infinite product over primes, or more generally, some set of primitive elements P, in terms of which the L function can also be written. So this is a different representation than this, but it tells you that basically, this is responsible for the connection of Riemann zeta to these prime counting questions and so on. Okay, functions like the Riemann zeta function are the kind of paradigmatic example, but there are other functions that we physicists find reasonable that are in a wider class than this. So the Hurwitz zeta function, so you just take your Riemann zeta and you shift in the denominator, then that actually does not have an Euler product. So mathematicians consider functions that don't exhibit all these traits, but the nicest ones have this property, and depending who you seem to ask, the Euler product is or is not the central element of what defines an L function. All right, so I want to talk about a few main open problems in the land of L functions, just to motivate again why this is interesting and why you might want to care. Depending on interest, we can go faster or slower, but this will take probably just a few minutes anyway. So the main one maybe is where are the zeros of L functions? So the Riemann hypothesis, or its cousin, the grand Riemann hypothesis, says that essentially for all L functions in a certain wide class, all the non-trivial zeros lie on the critical line, which in normalization I showed before is real part of S equals a half. Okay. So all these dots are meant to represent Riemann zeros. This is not proven. Remains an open problem. And I think it is believed that this will remain an open problem for quite a while, although everyone believes that it is undoubtedly true. These zeros exhibit various beautiful properties. So these authors here noticed that the pair correlations amongst the locations of the zeros exhibit random matrix statistics. So this is basically a plot of the sign kernel from random matrix theory. These points are the probability of finding zeros at a certain separation. Separation is plotted on the x, probability is on the y. This measures that degree of correlation between, say, if I have a zero at some location, what's the likelihood I have a zero x distance away along the critical line. And there's some beautiful match with random matrix theory. So that's a whole set of works there. And that extends beyond Riemann zeta to all kinds of functions.
Yeah, is that sort of understood from first principles?
I just observed, yeah. So I've tried to ask this about mathematicians, of some mathematicians. In the first place, there's some assumption of Riemann hypothesis in not making these experimental observations, but if you want to try to explain this, even talking about the distance, it assumes that you're on the critical line and you're just going up. So if there were off critical zeros, it would be clear how they sort of fit in this framework. So yeah, I think that proving the random matrix universality of the Riemann zeta zeros in some like rigorous way is like even further off.
Could you prove it assuming the Riemann hypothesis?
Sorry?
Under the assumption that the Riemann hypothesis is true, can you?
Yeah, I think even then it's not. No, well, so the mathematicians do not consider that proven. We, amongst ourselves, might think this is a done deal. No, but I mean, it's clear that they exhibit the statistics, but just forgetting about whether you're talking about the Riemann zeta function or just like any quantum system, somehow proving that it has random matrix statistics. That's like hard. Usually it holds in some asymptotic regime of energies or something in the physics setting. And so there are statements, conjectural statements about how every chaotic system exhibits these properties. That's this BGS conjecture. But I think proof of this in any way, even we would call it proof, is probably not really possible right now.
But even here, is this also true, like for the real zeta function? Because they also say this autocorrelation they plot at some insanely high 10 to the 20 zero. This thing. So if you go to the lowest ones, do you get some special behavior somehow? And so the things are not quite as steep.
Yes, so if you are low on the critical line, then I think you exhibit strong deviations from that behavior. You have to go sufficiently high in the critical line, but probably you don't have to go all that high. But well, okay, there's not really a scale. The problems are high, low is a little bit unusual to say, but yeah, here indeed, they're looking at a neighborhood of the 10 to the 20th zero because, well, the higher you go, the more you expect these kinds of statistics because, well, it's like a semi-classical limit. One of the things that I like about this story is that, well, some of the questions the mathematicians ask about L functions seem to sort of make physical sense, as I alluded to before. So one of them that's kind of fun is, in certain classes of L functions, they ask, what is the highest, lowest zero possible? So how high can you push this first zero? That's a fun question. It's a bootstrap kind of question. Right? So the answer is like 22 and change. Okay, but yeah, so for Riemann zeta, it's like 14 and change, but a certain more wider but relatively mainstream classes of L functions, the answer apparently is 22. But it's nice that they ask these questions. It made me want to read more. Usually in math papers, and I want to read less. Okay. All right, so another thing they talk about is subconvexity. I will come back to this later, so in the interest of time, let me skip that. It's a statement about how the L functions grow as a function of t as you go high on the critical line. Talk about that later. They talk about central values. So as you take S to a half, so vanishing imaginary part, how does the function behave? Are there zeros at the central point, S equals a half? If so, what is the order of these zeros? There are these connections to arithmetic and point counting and elliptic curves. That's the so-called BSD conjecture. There are beautiful conjectures about the distribution and value of the Fourier coefficients A sub n, involving the Wigner semicircle distribution. There's a lot of work trying to prove various conjecture properties of these things, and apply them even to some mathematical physics questions, like the so-called quantum unique ergodicity conjecture, which is a statement about, essentially about sort of chaos in certain certain shaped domains. Okay. So this was meant to be motivation for why you might care about L functions. Now we're going to talk about the 2D CFT side. Our starting point will be the Virasoro primary partition function. So take our z of tau, this is just trace of e to the minus beta h minus mu j over the full Hilbert space, and I'm going to multiply it by this factor of mod eta squared times root y. That preserves modular invariance, but gets rid of the Virasoro descendants. So now we're just counting primaries. In terms of x and y, which are the real and imaginary parts of tau respectively, we have a sum over spins, and in each spin we have a sum over degeneracies, weighted with the Boltzmann factor. And this prime is a sum over primaries, which is a notation that we all should use because it really makes a lot of sense. Okay, so where are the L functions? At first, it's not clear because, well, whereas familiar modular forms have a single constant that characterizes each Fourier mode, yet there's a lot of data for each Fourier mode. So at spin j, there's an entire infinite spectrum of primaries marked by dimensions delta. And so, whereas, say, in a certain class of non-holomorphic forms that called Moss-Kusk forms that are relatively well understood, there's just one coefficient. So you can't obviously take this data and turn it into some Dirichlet series. We might try to construct a spectral zeta function for the primaries. So just sum over all delta, construct this object. But as we know, d of delta grows exponentially like e to the root delta at large delta. And so this is badly divergent for any s. But it's not clear this makes sense. There's some vague motivation for what to do, which comes from some recent work I and others have been doing about 2D avatars of random matrix theory. The motivation is vague, and I won't spend too much time saying where this comes from, but personally, this is sort of what led me to it. We've learned that if you take a partition function, you can split it into two manifestly SL2Z invariant pieces. This is sort of the light data plus a bunch of modular images, and then this is what's left. And the piece that's left, called Z spec, well, it's called that because it admits a decomposition in a complete eigenbasis of SL2Z invariant functions. The Eisenstein series, its Moss-Kusk forms, the identity details not important. But the point is that this part seems to know about the chaotic fluctuations of the high energy spectrum. If you sort of look at the structure of the basis elements, you can write the density in terms of something that looks like a sum over periodic orbits, which is what people do in the world of quantum chaos. And so you can think of this as sort of capturing the fluctuations here in green around the sort of semi-classical Cardi asymptotic, which is the dotted line here. So to me, this suggested that maybe L functions somehow live in this spectral space, where sort of L of S, the S is the S of the eigenbasis. And so that's actually what we're going to do. The follower knows from that. So here's a prescription in 2 slides to construct something which is formally an L function from any 2D CFT partition function. So you start with the partition function of interest, ZP, and you subtract some putative partition function ZP prime with the same light spectrum. So ZP minus ZP prime just sums over heavy states. So the light part cancels, and you have the heavy operators you're interested in minus the heavy operators of this other fiducial object ZP prime. So ZP prime can be another CFT with the same light spectrum, like robust CFT, or it can just be something that is a fiducial object that does the subtraction correctly that you design. But what's left, just sums over heavy states, just with this kind of subtracted piece. And neither of these two terms is SL2Z invariant, but by construction, the difference is because each of these pieces is. For this talk, heavy means dimension greater than C minus 1 over 12, because the resulting object admits a spectral decomposition that has support just on that part of the spectrum, because as you go high on the fundamental domain, the function decays exponentially rather than growing, which is a condition needed for this technology to work. So as I was just saying, if you demand that this function be square integrable in the fundamental domain, then you can write it in this spectral basis. This condition is guaranteed by the subtraction if each of these were a unitary partition function, because unitary partition functions you can prove are analytic away from the cusp. So if you cancel all the terms that diverge at the cusp, you're left with something which decays at the cusp and is finite everywhere else. So that means it's square integrable in the fundamental domain, and the divergence got removed.
So you need to know that there exists this ZP prime that has the same light spectrum, that has a different heavy spectrum and is modular invariant.
Yeah, so you need to construct such a thing or assume that it exists.
Yeah, but I mean, does it? You know that it's by hand, you want to use ZP, I know there is such a.
Yes, so I'll mention that in a moment. As a conceptual point, though, if you're trying to do some bootstrap thing, then the strategy becomes to assume that it exists and then ask under what conditions the difference is necessarily trivial. And then you learn that there's only one such object that can have the properties that go into it. That'll be what we do later.
But you will find a solution that's not true.
Yeah, hopefully it'll be clear later. But for now, just given some ZP, you don't need to assume something fine-grained about the space of CFTs. You can construct some ZP prime, which gets rid of the light states and preserves modularity, and gives you this condition that leads to the fact that you can write it in this special basis, square integrability condition. Okay, so let's focus on the scalar mode, and you can write the scalar mode, so, right, so these psi's, these are just these basis elements of this thing. All we need for the rest of the talk is to know that if we look at the scalar for a mode, so the spin zero piece of this subtracted partition function, then it can be written as a constant term, which is the integral of this thing over the full fundamental domain of SL2Z, plus this inverse Mellin transform of the Peterson inner product between Z and the Eisenstein series. So in the spectral decomposition, this is just the Eisenstein part, and you look at the spin zero mode of the Eisenstein series, which is just the power of 1. The Moss cusp form piece does not participate in the scalar mode, which makes things simpler. Okay, so we've constructed this, we've looked at the scalar mode, and we noticed it can be written this way. And now comes the fun observation. The overlap obeys a functional equation, that much is known. So as S goes to 1 minus S, the Eisenstein series obeys a functional equation, and that implies that the overlap itself does as well. And it looks like this. Remember, this was this completed Riemann zeta function. Doesn't terribly matter for now. But if we define L as the product of Riemann zeta of 2S times zeta z of S, where zeta z is related to the overlap like this, then L is an L function. That is to say, it obeys precisely the right type of functional equation. So going back to before, we should define the completed L function and ask that it obeys the functional equation involving a gamma factor, not some other function, but it needs to have a gamma factor of the right form. And indeed, it does. So if you define your completed L function like so, there's a product of 4 gamma functions here with these parameters, then this object is invariant under S goes to 1 minus S. And this defines a self-dual degree 4 L function with this universal gamma factor and root number plus 1, which is the 1 sitting in front here.
find it by ansatz or like,
Well, no, it's just some massaging of this, which is well known, I've known for a while based on playing with these SL2Z spectral decompositions. But you know, it's not obvious from here. But yeah, after some defining, it pops out.
The curly Z was. Curly Z is what?
Curly Z is the difference of partition functions. So we have the subscript on L to remind us that it's attached to this difference of partition functions. And a better answer to Enrico's question is, well, see in just a moment that these aren't totally arbitrary. So in particular, here's the scalar mode, and if we expand at large Y, now we're just writing the sum over states. And the overlap needs to be such that you actually reproduce a sum over states in a compact CFT with a discrete spectrum. And these factors are exactly those needed to do that. So it's not just made up. Great. This is me saying that. So it's useful for physical intuition to think about the Dirichlet series associated to this object. It is just packaging this information about the subtracted heavy scalar spectrum. So we have some frequencies lambda, which are just the subtracted scalar dimensions with the here by subtracted, I mean C minus 1 over 12 pulled out. And so having canceled all the light states, right, this thing just has support on the heavy spectrum. So we have some spectrum of frequencies lambda. There's some lightest one lambda 1, which is positive, and the rest is unbounded, and the lambdas go all the way to infinity. These are just scalar dimensions with C minus 1 over 12 subtraction. And the numerators A are the difference of degeneracies between sort of ZP and ZP prime at that dimension delta. So this is the spectral zeta function for the scalar component. It's a generalized Dirichlet series. And the point is that the relation of this object to the overlap is like so. This is exactly as it must be, such that if you develop the large Y expansion of this integral, say by you deform the contour to the right to pick up large Y, you see that it's a sum over exponentials times root Y, where the dimensions appear in exactly the right place. So this is the form of the scalar partition function, and the form comes out correctly after this series of definitions. Okay. Now you might ask when this is more than a formal series. We haven't talked about convergence yet, and by construction, we've canceled the light states between these two partition functions. So by modularity, you've also canceled the Cardy density of heavy states and all the exponential corrections coming from other light operators. So you would generically expect simple convergence, but because Cardy's an integrated statement, you have to be a little more careful. We'll come back to that later. Okay, so I was asked about the subtraction. So here's one canonical way to perform the subtraction. So for every light state, you can subtract a unique linear combination of modular J functions that gets rid of that state and introduces no other light states and preserves this square integrable property. So we construct the ZPJ, which it's a different, so this is our ZP prime here, constructed in a particular way, where for every operator in the original partition function, you sort of replace it by this sort of Hecke-like operator, which is just a sum of J functions, J and J bar, a finite linear combination, which is defined to just give you the same power of Q and Q bar that you're trying to cancel, plus strictly powers of Q, which are strictly in the heavy part of the spectrum.
How would this work if you looked at spinning, or if you also included spin?
Yeah, so it does work. H and H bar differ by an integer, then you have some terms that are, say, like where the number of J's and J bars differ by some integer. And you might even have some negative powers of one or the other, but you always have more positive powers. So the total number of J's and J bars is always positive. And for that reason, this thing is non-singular everywhere in the fundamental domain, and therefore preserves this L2 property. So because J is modular invariant, and because we're respecting spin quantization, the resulting thing after subtraction is also modular invariant. It's manifestly discrete. And as I just mentioned, it doesn't add new poles, even though you might have the negative powers of J bar, you have more positive powers of J. And one feature of the J function, which is not trivial, is that sort of if you have a zero, the zero is a unique zero in the fundamental domain, it's on the boundary, on the unit circle. And so if J is zero here, then that's J bar is zero here. And so you have this cancellation of zero such that you just get zero instead of a pole when you have a total positive number of these guys. The details of this aren't supposed to be immediately absorbable unless you work with this stuff carefully. But the message is simply that there's a canonical way to subtract these light states by constructing something which is not supposed to be like a bona fide CFT partition function and isn't necessarily unitary or positive, but definitely respects this property for these reasons. Okay. Let me pause and ask if there are questions. We're going to talk about some of the analytic structure of these things, but let me just make sure message is coming across.
You have some explicit like examples where you can do this like and so on.
Yes, yes and no. Okay. So the thing about Virasoro CFTs at central charge greater than 1 is that we don't have any partition functions in hand at all, unless there's a larger chiral algebra in the game, in which case the partition function is rational with respect to that guy. So, for example, maybe the closest thing is that if you take C free bosons, these are these sort of, you put them on a Narain lattice, there's the so-called Narain CFTs of central charge C, which is some integer. These are free CFTs, but so they have lots of extra currents. If C greater than 1, you have a U1 to the C current algebra, which is larger than Virasoro. So from the Virasoro point of view, the theory is like irrational, but has extra currents, so it's not really a bona fide example of something that looks like a generic CFT at all. There's lots of extra structure and it's not chaotic, etc. So we don't have any examples to play with that look like the ones we want to understand, which is part of the motivation here. But for the Narain case, you can construct the L functions, and they are certain Eisenstein-like zeta series, and it's helpful for orientation for some of this, but maybe at a formal level. Yeah. Okay. So, all right. Now, obviously, one should study the analytic structure of such a function because that's what you do in number theory when you have an L function. Let me not try to sort of explain where it comes from. In the interest of time, I'll just show as a picture of where they are. So now we're talking about the analytic structure of the L function L, not the completed thing. Remember, the completed thing just has, well, they're obviously related. But let's talk about L here. So there's a single pole at S equals 1. It's a simple pole. This is due to the fact that if you integrate this difference over the fundamental domain, you'll get something non-zero. This is called the modular average, assuming it's non-zero just for genericity, and it leads to a simple pole at 1. That's the only pole. And that's a statement about discreteness of the spectrum. If you had extra poles, say in the critical strip, then in the Y expansion, the large Y expansion, they would lead to terms not compatible with this sum over exponentials in Y. You'd get other power law suppressed terms. These are like powers of terms like log Q bar. This is not the structure of a compact CFT partition function. So discreteness forbids other poles aside from this one. The interesting thing is the zeros. So there are some trivial zeros, just like for Riemann zeta at these half integer space locations, at a half, minus a half, minus 3 halves, they're simple. There are possible zeta zeros, that is Riemann zeta zeros. So L can have zeros at sort of the location of the zeros of the Riemann zeta function divided by 2. So at sigma equals 3/4, 1/4, you can have some zeros here, but they need not be there. And then there's some non-trivial zeros, which I call rho and t. And those are dependent on the particular theory. And I don't, in general, even know where they are not allowed to be. So it's not a setting where the Riemann hypothesis should hold. I don't know anything about whether they are confined to some critical strip something like this. But in general, there will be infinitely many of these. And I also don't know whether they are necessarily simple. What I do know is that they come in sets of 4. So if you have a 0 here, there's also one here, here, and here, by way of the functional equation. All right. So these, let's translate this a bit into some CFT and get back to the physics. So let's think about the Dirichlet series from before. If we ask ourselves, what is the meaning of the trivial zeros? These were at s equals a half, minus 3 halves. And so if we think of that as some statement about the sum over frequencies lambda, then this is the regularization or analytic continuation of the moments of A. So you sum over the frequency, the generacies A weighted by integer powers of lambda. And the statement that this vanishes is the statement that all of these moments vanish in the regularized sense of analytic continuation. Right. So that's kind of interesting because A is a subtracted density of states. So what it's telling you is that if you cancel all the light states, then on average, the heavy spectra are the same. The heavy spectra cancel too, whereby on average, I mean that all the moments vanish. So this is something you can think of as a strong UV-IR relation in 2D CFT. If we ask what's left in the UV after we cancel this light stuff, the answer is, well, A of lambda is non-zero, but if you do these averages, it actually vanishes, again, in the sense of regularization.
This is like stronger than the Cardi formula. So the Cardi formula is sort of part of the, so it's like.
Yeah, this is stronger than the Cardi formula. Right, so it's like saying, it's like asking what's left after Cardi cancels. And the answer is small fluctuations, but in this sort of average sense. But just to make the point clear, I mean, definitely A can be non-zero, right? This is, first of all, it's an average statement, and second of all, it's really regularized statement. I mean, this thing, so the Dirichlet series has this pole at 1, and when it converges to the right. So we can't actually continue the series past that. And the fact that there's this analyticity, this lack of poles to the right of s equals 1, can be thought of as what's called square root cancellation. So if we again take the Dirichlet series, remember, I defined it with a s minus a half in the denominator. Excuse me. So s equals 1, it's a half down there. And so the statement of the absence of poles is this one here. And so you see that the A's sort of have this 1 over root lambda fall off as a result of this statement. So that phenomenon that you have cancellations in the sum over coefficients that buy you a square root's worth is called square root cancellation in number theory. And actually, the Riemann hypothesis can be phrased as a statement about such cancellations for this Mobius function, which sort of takes plus and minus 1s as you vary n. You sum over a bunch of these, and you go out to large capital N, and this goes like big O of n to the 1/2 plus epsilon, where that means, maybe logs. So that's also another form of this kind of heavy cancellation. All right. Now, having articulated where the zeros are, we can write a factorization of this function over its zeros, just as a statement about complex analysis, and this will be useful later. So let me just state it. The completed L function has these poles at s equals 0 and 1, and it's what's called a function of order 1, which means that as you go out to infinity in any direction in the complex S plane, it doesn't go faster than e to the s log s, or mathematicians will put it this way, it doesn't go faster than e to the s times something which grows slower than any power of s. And that implies that there's a factorization over the zeros, like so, with power 1 here generically, although you count with multiplicity. So these non-trivial zeros from before. And then there are these Riemann zeta zeros that might be there. I've sort of split the Riemann zeta zeros row into bold row, which are the ones appearing here, and bold row prime, which are the ones that aren't. So at least some subset zeta zeros can appear in this factorization. And you might be familiar with these kinds of factorizations in other contexts. Usually you have some exponential factor coming along for the ride with each zero, some e to the s kind of thing times some coefficient. But those actually don't appear here because of the functional equation, which is the invariance of the s goes to 1 minus s of this whole thing. So it's actually kind of a nicer object, and it is easier to understand the large S asymptotics, for example. Okay. Just to underline a conceptual point, this makes manifest that we can trade thinking about the spectrum delta for thinking about the spectrum of zeros rho. This is something I hope to try to make hay of more in the future, but it would be nice to understand CFTs in these terms. The first order of business, I would say, is trying to understand where the non-trivial zeros are really allowed to be or not allowed to be. Okay, so this is the sort of summary of the features of this object so far. Attached to every compact unitary Virasoro CFT is a self-dual degree 4 L function, has this universal gamma factor, root number +1, and a simple 0, the central point. Or something so that vision would highlight. Let's skip that comment. So some comments. So this is one version of this statement that we have some object which obeys a functional equation, but it only knows about high energy states. So this is a constraint that just acts in the high energy sector, albeit with the subtraction that was necessary to make that possible. Just to stress, the gamma factor doesn't depend on the theory, it just depends on the fact that we're looking at the Virasoro party. You can generalize beyond Virasoro. So if you take your theory to have extra currents, say n currents, which form a larger chiral algebra, so Virasoro n would be 1 here. You can think of this as the number of generating currents of the algebra. Then there's a similar story. Now the frequencies are just, you look at the full partition function for the primaries under this maximal algebra. The frequencies now get some extra shift. Their n, the central charge gets a contribution from n currents. So you strip that away. And now you get a degree 4 L function again, but the kappa factors change to pick up some n dependence. You can try to run this for other torus observables. There's no obstruction to doing so. I haven't done that. You should. And one last time, the fact that spectra are 0 constructible means that we should try to understand what to do with that from a physics point of view. That's what this sort of picture is meant to represent. There's something on the math side called the approximate functional equation, which I think could be powerful here. Basically, you take the Dirichlet series, you cut it off at some high frequency, and you sort of leverage that, what you know about the low frequencies, using the sort of this equation into a fuller knowledge, excuse me, of the high frequencies. There's some way in which you can do that. And so I'll say at the end is what I sort of have in mind about how to use that in a CFT context. If you know about the Riemann-Siegel lookalike formula for the Riemann zeta function, it's a version of this. Okay, so on the gravitational side, and not to linger too much in the interest of time, I want to talk about the rest. I mean, there's some sort of direct translation of what I've said into statements about black hole microstates. I would only emphasize that you can think of this as a question about UV completion of an effective field theory in the bulk, and the space of L functions as being the space of, UV completions given some fixed EFT, in the sense that some fixed light spectrum is subtracted off. What's left is some L function with the properties we've been discussing. So that's some more quantitative characterization of the freedom in the UV that's left. And so we can rephrase the constraints we discussed earlier about UV-IR relations in this language, which makes contact with problems people talk about in the swampland literature. Okay. I'm going to skip this random matrix universality subconvexity thing, but I'm happy to talk about it afterwards. All right, let's talk about modular bootstrap. I have 15 minutes left or so. Is that accurate?
Yeah.
Okay. Great. All right, so for those who aren't practitioners here, let me summarize modular bootstrap state of the art. So again, modular bootstrap is trying to put an upper bound as a function of C on the dimension of the lightest Virasoro primary operator, I'll call it delta 1. The subject was started in a paper by Simeon Hellerman 16 years ago. He bounded delta 1 from above by C over 6 at large C. That was improved over the course of the decade to C over 8.5 analytically, and C over about 9.1 numerically. But it's always been expected that the real bound, the optimal bound is C over 12. And the reason is that in IHES CFT, large C CFTs are dual to semi-classical gravity, and IHES gravity always contains a spectrum of BTZ black holes, and modulo quantum effects near the threshold for small black holes, the spectrum of BTZ black holes starts about at C over 12. And so every such theory is believed to have this spectrum of black hole states. So on the CFT side, you should always have some heavy states starting at C over 12, plus or minus. There's been a lot of progress in different kinds of regimes where people bound the twist, which is the dimension minus the spin, rather than dimension. Some nice connections to sphere packing were unearthed in this paper. And a U1 to the C analog, as opposed to Virasoro, has actually been proven for the average Noreen CFT. So the typical Noreen CFT, typical with respect to the Zamolodchikov metric, was proven to have a gap of order C times a coefficient, which is the U1 to the C analog of the Cardy function. But progress toward this has stalled. And so you might ask, why is there a bootstrap bottleneck? And we don't completely know. But let me just make a sort of philosophical point, which is that in bootstrap circles, it's often believed that we can just do pure modular bootstrap, where you combine unitarity and modularity and nothing else. And if we do this well enough, we can actually bring the bound down to C over 12, despite the significant efforts of people so far, who are very smart indeed. But I'm not sure that's justified. If we just ask ourselves, what are the reasons for believing that? Is it more of a superstition or wishful thinking, or are there good reasons? And we don't know. The obstruction might be technical. So when you got to large central charge in that approach, there are challenges to getting the algorithm to converge. The functional methods and the large central charge limit don't play well with each other. Harnessing full SL2Z is not something we really know how to do. But there could be some conceptual obstruction. And the point I want to make is that the only solid argument for C over 12 comes from gravity. And gravity is a special theory with lots of properties of the states above the threshold. So it's maximally chaotic, it has random matrix statistics, it has maximal scrambling. And so it could be that we need to use some properties of the states above the threshold to bring the bound down to C over 12. Maybe the totally general bound is not C over 12, but if you add something about the high energy spectrum, or at the very least, use some of these more fine-grained properties of the density of states, then perhaps you can bring it down. Okay, so what's the logic of what I'll try to explain here? So we're going to imagine taking the L function attached to some curly Z, which is the difference of primary partition functions, each of which has a gap to at least C minus 1 over 12. So there's the vacuum module, and then nothing, C over 12. And you take the difference, and so we have our L function. And so if the lightest frequency lambda 1 is bounded above by some lambda star, then this implies that the scalar spectra of Virasoro primaries obeys this bound, C minus 1 over 12 plus lambda star, modulo one possible exceptional spectrum. That exception comes from the fact that you're studying a difference. So one of the spectra could be arbitrarily high, and then the other one just has to meet this bound. But if there are two spectra which are unbounded, then you take their difference, run the argument, and then there would be no bound. So there's one possible exceptional spectrum, which is kind of funny. But if you can prove such a bound, then you infer this scalar bound modulo this one possible exception for all CFTs. But more generally, the result is one of spectral determinacy. If I take two partition functions with the same light spectrum and the same scalar spectrum below this gap, then they must be the same. because the difference vanishes. That's something we call spectral determinacy in this paper with UCLA alumnus Justin Keide from about 5 years ago, where in the context of rational CFT, we used a similar strategy, thinking about differences of partition functions. In the interest of time, I want to explain that story. But now we're going to do the same thing, and we're going to do it in this L function form. So the idea of what I'm about to prove is to play these two representations we talked about before off each other. There was this, on the one hand, this Hadamard representation, this product over the zeros. And on the other, this Dirichlet representation, which was this sum over frequencies. And so the question is, can we drive up the lowest frequency, lambda1, while maintaining a consistent set of zeros, rho, over here? Sure, all these things must be equal, and you can try to leverage the respective properties to make a statement along those lines. A number of theorists told me he thought that was a weird thing to do, which I felt gave me the motivation I needed to proceed. It's good to do something that they not thought about or would find strange. Okay, so in what follows, I'm taking the L function to be that of the large C limit of some sequence of theories, and thinking of lambda1 as becoming parametrically large in C. So, for example, lambda1 scaling with C, if you could show that lambda1 can't scale more than, say, root C, that would already, the leading order, you'd be done, right? Because then the bound would be C minus 1 over 12 plus order of root C, which is leading order, just C over 12. In any case, we're thinking of lambda1 as being parametrically large in C. We're going to bound it above using an argument like this. Now, the statement about, since I'm going to be working in the parametric limit, I'm going to be making statements about lambda1 being bounded parametrically. We have to think of this so far as a statement about sort of working at large C. It would be great to turn this into an algorithm for bootstrapping at finite central charge and then showing that as you take the large C limit, you actually land on this statement. I haven't done that, but I think it's important to do that. Okay, so let me sketch the proof, and happy to talk about it more afterwards, but the idea is to take the log derivative. On the left-hand side, you have the sum over zeros rho, and on the right-hand side, you have sort of Dirichlet series, the log derivative of that guy. And I've pulled out the leading frequency, and so zeta hat is just some Dirichlet series where I've pulled out the leading frequency. So this starts at frequencies lambda hat equals 1 and goes on up. So the idea of the proof is demonstrated by the following warm-up. Suppose for a moment that these two functions of S were just not there. And at large lambda1, we could suppress them, and we have an equation like this, which we need to solve for all S, where we can make this equality. But there's no such solution to an equation like that. One quick way to see it is that the functional equation tells you that the log derivative is odd under S goes to 1 minus S. So the log derivative can't equal a constant. You can see this in a more hands-on way by looking at sort of the large rho asymptotics of this sum. You might say, well, why not? What if I just look at the sum over zeros, whose magnitude is much greater than some fixed S, and you get this, and this involves using the self-duality property. You have 4 zeros for every 1, they come in the sets of 4. And so first of all, you get this S minus a half out front. You can't sum over them to get a constant in S. And also, you can show that this sum is necessarily finite, so you can't solve this equation. And so the idea of the proof is to validate this approximation for some appropriate range of S. In other words, to show that there are values of S, a complex S plane, where you can drop these two terms, and so large lambda1 arrive at a contradiction. Let me not explain that in such great detail, but the spirit of it is this. So this is a valid approximate equation for all S in what I'll call a zero-free region, R infinity, which is parametrically less than root lambda 1. So in other words, the zero-free region, by that I mean a region where there are no zeros of the L function. And so this approximation holds As long as there's not a parametrically large dense disk of zeros, in other words, as you take large lambda one, as long as the L function doesn't fill some disk of radius root lambda one with zeros. So if I sit at some S parametrically less than root lambda one in the zero free region, so the left-hand side is not blowing up, right? And at some uniform distance from the nearest zero under these conditions, then the claim is that you can drop those two terms and you arrive at this approximate equation, which therefore leads to the bootstrap bound by the contradiction that I mentioned earlier. So one just needs to establish that a zero free region exists. In other words, if there's not this dense disk, that you don't have to go out to parametrically large S of order root lambda one or greater to be in a region where you're not sitting on a zero. But that actually just follows from a property of entire functions of order one. So if you look at the number of zeros row inside a disk of radius r, for a function like this completed L function, then this is bounded to be no greater than r dressed with logs, r to the 1 plus epsilon, as you take r, the radius of the disk, to infinity. And so that means that the density of zeros inside the disk is going to 0 or large r. Because the area of the disk is r squared, the density decays roughly like 1 over r. In other words, the zeros are sparse. The average unit cell contains no zeros at all inside this disk. So it's very easy to find a zero-free point inside this very large disk. This, by the way, is this general property of functions with these complex analytic behaviors at infinity. There's a more hands-on way to see this. Essentially, larger gap means fewer zeros. But there's some sort of bound on how that goes, and indeed, in certain situations, you can show that lambda one is actually bounded above by a half. Although that situation, it's a complex analytic constraint on the number of zeros. It's not some kind of transparent CFT condition. So I'm certainly not claiming to have proven that actually bound is C minus 1 over 12 plus a half. Although there's some interesting stuff to explore here. Okay, so let me mention a check that this strategy passes, and then I'll basically conclude. You can try to run this argument in the rain CFT. So as I mentioned before, the typical gap is of order n. As I also mentioned before, if you have n independent currents, then the L functions sum over frequencies lambda, which are related to the dimensions delta like this. Now in the rain, C equals n exactly. So this is 0. And so it must be that lambda 1 can be of order C, because we know that lambda 1 is just delta 1 in the scalar sector. And delta is allowed to be of order central charge. So there must not be an argument that forbids us from driving up this frequency proportional to central charge in that setting. And the argument does fail, because the gamma factor depends on n. So now we have an equation like this. This is just, again, the log derivative in terms of the zeros, now in terms of the zeta series. And this Fn now depends on n. If you take large n, this goes like log n, which exactly cancels this when lambda 1 is of order n. So there's no way to manufacture this type of equation where you have sum over zeros equals large negative constant. That cancels the one from here, and you have to use the S dependence, and the argument fails. So I find this to be a comforting check on the strategy, even if it still appears kind of foreign. Okay, so this was the spirit of the argument. There's this tension between the gap and the density of zeros, and you can't have a large gap and a sparse set of zeros. Let me sort of, although this is important, let me simply, in the interest of time, I don't want to run over, just say that the argument involves assuming that the spectral zeta function converges for finite S, and that's not necessarily guaranteed in a completely generic setting, because plot the frequencies on the x-axis, and we just make some drawing of how the degeneracies between theory Z and theory Z prime might look. Imagine we have some support here. And generically, so these are the sort of it's the difference in generacy. So here, these are the Ds. And so the other guy, which contributes negatively to the density, which I'm kind of plotting here, would have degeneracy somewhere else. And so generically, as you take a difference, if you look over some window, which is not too small, there's going to be a cancellation between these two. And you can show that leads to convergence of the zeta series. But it's possible in principle to have a situation where you have something like a chiral CFT, where the degeneracies clump up hugely at some regular intervals. So in a chiral CFT, the Carty growth is sitting all exactly at some point, and the spectra are regularly spaced in every chiral CFT. And so in this case, the zeta function may not converge because as you include more and more states, there's some very erratic behavior every time you hit one of these spikes. So the assumption of convergence is in some form an assumption that the spectrum is chaotic. In other words, that the spacing between successive states is not anomalously large, which is closely related to imposing finite degeneracy asymptotically a large delta at any fixed energy, which is something I think we should try to think more about, because after all, degeneracy is the opposite of level repulsion. And I think thinking of it in those terms really urges us to try to understand the consequences of demanding that even at asymptotically large delta, we have no more than one state at any fixed energy. I'm hoping this is sort of a step in that direction to think about the consequences of that for CFTs, but it's a nice setting in which we actually see that chaotic behavior actually leads to something in a bootstrap kind of argument. Let me finish there and just say that there's some stuff to do, clearly. I think it'd be nice to understand the L function of gravitational theories we're interested in and the properties of zeros in those theories. And perhaps to understand whether CFT spectra are actually built out of some set of primitive dimensions, which would really be wild, but because L functions in Euler products, it's something that one should at least entertain and try to look for, even though I don't think these objects should have any right to have an Euler product, but who knows? So anyway, thanks.
Zeros may have no black hole with a 20. Right. I don't know how to compute a zero, but in some holographic.
No, that's a great question. I don't have any idea. Yeah. Yeah.
So how should I understand this behavior, this chaotic behavior of the spectrum at like high central charge? So that like you go kind of in the classical limit. So you say like that thing, the system, like the air is described as a classically chaotic system to still have this like level of motion type setup there.
Well, you're alluding to something which has been hard. No one's really made precise for CFTs, which is that in more familiar like quantum chaotic settings, the statement is if you have a classically chaotic system, its quantization exhibits random matrix statistics. But there's no notion of classically chaotic, for CFT. You just have some quantum thing. And I don't know. So therefore the CFT version of this BGS conjecture, which relates classical chaos to random matrix statistics after quantization, is not, you can't literally put that structure on CFTs. So the question is, what form of random matrix universality is supposed to hold for 2D CFT? This is open. So it should at least include this linear ramp in the spectral form factor after you account for Virasoro symmetry and look in the sector of fixed spin. If you look at the 2-point function of the density of states, this should have this level, this spectral rigidity, which manifests itself in this linear ramp of the spectral form factor. This is kind of like the simplest hallmark of any random matrix universality in any system. But whether stronger forms of that should hold for 2D, and in what regime of energies and at what rate do you approach that as you look at large delta? These are interesting open questions. So for example, the one thing you often see in that literature is that people see this. People plot the nearest neighbor spacing S against the probability D of S. And there's this, in random matrix theory, this so-called Wigner surmise for this this function, which is depending on the ensemble or something like that. It's an infinitely long tail. So you sometimes see that people have looked at energy levels in some system. Originally, these are like hydrogen atom energy levels, and it's universal. So there's a lot of evidence that this happens very generally, but actually that the systems seem to obey this pretty carefully, or pretty closely. But this is a much stronger statement than the linear ramp in the spectral form factor, because it actually involves knowledge of all endpoint correlations. A nice way to think about that is that this is the nearest neighbor spacing. You're asking about the probability that you have an energy level here and say an energy level S away with no others in between. So actually you need to know all the endpoint correlators to know this, but whether this should actually be a property of CFT spectra at large delta, I don't know. That was kind of a long answer to your question, but I don't know. I like this topic. So.